Okay, so when we did all those expansions for the discovering patterns in the first section, okay, so we noticed some sort of pattern happening with the coefficient. Okay, so when we had 1 plus x squared, we had the coefficients as 1, 2 and 1. We had 1 plus x to the power of 3, we had 1, 3, 3. 1 plus x to the power of 4, the coefficients were 1, 4, 6, 4 and 1. Okay, so what we're going to do is arrange those coefficients for 1 plus x to the power of n can be arranged in a triangular pattern which we call, which is called, Pascal's triangle. Okay, so we've got 1 plus x to the power of n. Okay, so when n equals 0, we're starting with the just the coefficient, not the variable. Okay, and of course, when we have this to the power of 0, we have 1. Alright, n is 1, so 1 plus x to the power of 1, and the coefficient, putting symmetry in the middle, 1 and 1. This is in your notes, by the way. I'm showing you. Okay. How it works. So we have a expanding of a square, okay, so the coefficient will be 1, 2 and 1. Okay, so as we increase from n, okay, 1, the triangle gets bigger and bigger towards the number of terms in that row. So 1, 3, 3 and 1 for the coefficients for that. Okay, 1, 4, 6, 4 and 1 for the power of 4. And we've just justified 1, 5, 10, 10, 5 and 1. Okay, so this pattern continues. Okay, so when we got n is 3, n is 4, n is 5, n as 6. Any ideas what that's going to look like? 1, good. Any ideas what the next number is going to be?
1, 6, 15, 20, 15.
Good. Yep, see how that works? So what's the 7th row? Well, 8th row, sorry.
1, 7, 19, 21, 35, 21, 7.
Okay.
21, 7.
21 here.
35.
Good.
21.
Alright, so it continues. So we have identified the pattern. Good. Okay, so Pascal's triangle has the following interesting properties. So the first one is the first and last number, apart from the very first row of course, where the first number is the last number, but each of the first and last numbers of any row is 1. Okay, so all along the diagonal, you're going to have 1. Each other number is the sum of the two numbers to its left and right in the row above. Okay, so I'm assuming you both have identified that. 21 comes from 6 plus 15. 4 comes from 3 plus 1, so we add the two numbers above it on either side to get that particular number. So we can continue that pattern to any value for n right the way through. Okay, the sum of the numbers in each row is 2 to the power of n. The sum 2 to the power of n. Okay, so n equals 0. So the sum of the numbers in this row is going to be 2 to the power of 0, which is of course 1. N is 1. The sum is going to be 2 to the power of 1, which is 2. N is 2. 2 to the power of 2, which is 4. 1 plus 2 plus 1 is 4. N is 3. So 2 to the power of 3. So 3, 6, 7, 8. 2 to the power of 3 is 8. Okay, so the sum of the coefficients. So the sum of the numbers in each row is equal to 2 to the power of m. Okay, so this one will equal 16, 32, 64, 128, and the next one will be 256, and so forth. Okay, quite a few patterns we can identify. Okay, so there are many other interesting patterns, but just for this subject, so just for this course, the three that I've just mentioned will be the main ones that you'll be looking at in the work that we do for this section. Okay, so examples using Pascal's triangles. Let's expand the following. A. Right. 1 plus x power 4. So previously we did 1 plus x to the power 2 times 1 plus x to the power 2, or 1 plus x times 1 plus x to the power 3. Okay, but we can actually use Pascal's triangle to get the coefficients in place, but we need to add the include the variable with that as well. So what is that going to look like? So we need n, we need the 4, n equals 4, n equals 4, we need 1 plus 4, and as we go from left to right, we increase in powers of x. 1 plus 4x plus 6x squared plus 4x cubed plus x to the power 4. Okay, nice quick way to expand those when we work out the pattern using Pascal's triangle. B. 1 plus x to the power 5. So you don't need the fifth row, okay? You need the row where n equals 5 because the row starts at 0. So you need the sixth row coefficient. Okay, so you grab n equals 5. This row here, so we need 1 plus 5x, 10x squared, 10x cubed, 5x to the power 4, and x to the power 5. Okay, and of course your power is equal to the power of your original question of your expansion. Okay, so if you get x to the power 6, for example, then you've not selected the correct row. Right, 1 plus x to the power 6. Okay, so we've already now established a couple of rows furthermore than what's in your notes. Okay, so you need to take the row where n equals 6. 1 plus 6x plus 15. Okay, and we have symmetry as well in the middle. Right, 10. We need to do a bit of work first. Okay, so before we can get at the 10th row, we need to have the 9th row. To get the 9th row, we need the 8th row. To get the 8th row, we need the 7th row. What we got here. Okay. Okay, do you agree? Do you even work it out, or you just trust my word for it?
Trust me.
Okay, so that is a quicker way compared to what we did the first section. Okay, 1.1. So while that allows us to expand the 1 plus x to the power of n much quicker than doing it algebraically, there's still a couple of fallbacks, okay? A couple of issues that can arise, okay, or have arisen already. So what are they?
Having a triangle.
Hey,
Getting the actual triangle.
getting the actual triangle to be able to do it. So you need to compute the triangle for larger powers of n. What's the other issue?
If they're not 1, the coefficient isn't 1 or the...
Good, the coefficients aren't 1, okay? So there's our two major limitation to the use of Pascal's triangle, okay? So this allows us to do a quicker way, and fortunately, we are also going to go another quicker way, that for any coefficient, value coefficient in here, okay, we were able to have the correct expansion fairly quickly compared to doing it algebraically. Yeah, any questions on that? Alright, so